Hi there and welcome to the last tutorial of the Mechanism Design project. In this tutorial we'll be just focusing on how we do a multi-bar mechanism in Simulink. So what we'll be doing is looking at doing this 4-bar mechanism where we have joints at A, E, B and C, and actually E to D, this beam is actually a solid beam, and the joint B to C beam is actually rotating about this point here. Okay. So we're going to be using all the same models that we've used before. We're just looking at how we join all of them up to make this mechanism. So what I'd recommend is to look at, once we follow this demo, you want to be able to make your mechanism of your convertible roof, all the beams in the right configuration and places. Look at creating your motor and gearbox feedback loop using a single mass and pendulum. Once you've got that feedback loop and you're happy with it, you will then be able to import that and add that to your mechanism system. Okay, it's good to try and keep them separate until you're happy with both, and then bringing them together at the end. Okay, so we're going to go and start completely afresh with this. So I'll move this down as our reference point. And we will open up mechanism blocks because we'll be using those. And what we also need to do is SM new to create our new model in Simulink. Okay, so we're going to start completely afresh. So if we go through all the steps of actually how we just set up the core part of our model, we will want to first go to our simulation model configuration parameters. In here we want to change the solver, so we want to change it back to a fixed step solver, and we're going to use the Running Cutter. Okay, so Running Cutter here. Okay, and we can click apply. And what we also want to do is change the time step to 0.01 seconds. Okay. In your reports, it would be really good to talk about Running Cutter and why would this be a suitable solver for your mechanism problem. Okay. What we can do is start to remove some of the features in our model that we're not going to be using. We can also go to display and unhide the automatic names so we actually see what we're working with. And also if we go to diagram and format, we can go to font styles of the model, and we can then select, say, 14 size fonts for the blocks to increase the font size to make it easier to read, and it'll be more suitable for when you're printing on A3. Okay. There we go. The last aspect that we need to do is then go to the mechanism configuration. So if we go to this, we can then actually change our configuration so the gravity is acting in our Y plane. Okay, so we just copy those across, change that to 0, make sure there's only a single space between them. That's right. So we've got X, Y, and Z as our vector there. We click apply, and now we've got gravity acting on our Y plane. Then it's a case of just starting to create the elements of the model. So the first things we're going to do is going to be point A and point E. So if we bring up our mechanism blocks, or actually we can start with just using the solid and rigid transform that I've kept when we deleted the rest of the other parts of the model. So to do point A, we just need to attach it to the origin. We can call it A, and what we're going to do is have it as a sphere, and we're going to have it as previously, we're going to have it as a 2 centimetre sphere. And for this case, we're going to just use a point mass of 1 kilogram. You can click apply. There we go. So point A, we can use brackets 1 kilogram, so we know what the mass is at that point. If we go to our simulation and update the diagram, there we go. We see that now we just got our single point in our space. We can then just cut Y up because that's going to be where our axes are looking, and we can just look with Y pointing up, X pointing out. It's in our positive direction. If we just move this to one side, and if you see the world frame, if you just double click that, we can see that it's actually just stuck on our origin. Now what we want to do is actually have a point E, and we want to move that 80 centimeters along, okay, from the origin at a fixed location. To do this, we can actually just copy A and use what we have here as the rigid transform. This is actually not like a joint, it's just actually doing a translation from one point in space to another point in space. So we're just going to attach it to the base of our origin. So it's going to say that's our reference point. We double click this, we can then say we're not going to be rotating, we're just going to be translating. And we're going to use Cartesian coordinates, and our offset in centimeters along the x direction is going to be 80. Click apply, and OK. And we just attach those to the point mass there. We can rename that E. So we've just copied and pasted that across. Okay, I'll do that. And then we update the diagram. And what we can see is now we've got A and point E 80 centimeters along. So that's how you can do a rigid transform along your in your Simulink space. So you might have that when you've got multiple points for your mechanism, and most likely you'll have a couple to be able to generate the mechanism that will deploy. Okay, so now it's a case of starting to do all the actual joints and add all the beams in. So let's say the first beam we're going to add in, or the first joint we're going to add in, is joint A, and we're going to also do the beam AB. Okay, so I'll copy and paste the beam, and we'll copy and paste the revolute joint. We then just have to join the revolute joint up. And what we're going to do is actually give it an ideal target that we want to do. So we're going to give it a high desired target, and we're going to say 120 degrees. Click apply and OK. And we are going to then just join this beam up to the revolute joint. Now let's rename that joint at A. And then we can call this one beam AB. A to B. And in there, we'll set it the length of 20. We'll give it a width of 1. And actually, we're going to give them some density. So in your example, you'll need to have an idea of how much mass, the mass of your mechanism. And as we don't know anything more about how that mass is distributed, a nice assumption or logical conclusion would be to uniformly distribute that across all your beam members and your pins or your joints. So for this density, we're going to, let's say, normally put it as 10 kilograms per meter squared. You can calculate that off based off the predicted mass of your mechanism. We click OK, and if we update that diagram, we'll see we've got now a blue beam coming off A at 120 degrees. So very similar to our beam here. So now it's a case of actually joining. Let's do B to C. So what we need to do is a new joint. And we can add that in. We can also give it we'll give it a mass, a point mass, so we can represent B. We'll give that B, and we'll give it a 1 kilogram again. Okay, joint at B. And we'll copy and paste beam AB and just add that on there. Okay, and we will then do change this to BC, and we need to change the length of this to 80. And what we need to be aware of and be careful of is actually we want to edit these joints again and go to state targets. And in this case, we do not want to specify a target. Okay? Because if you do, if you do that to all your joints in here, it'll try and make those all fixed. And the problem is your model might not be able to connect itself with all those angles. So you need to free those angles up and say, actually, I don't mind which angle that's going to be at, as long as it will connect up with all my other joints and beams in the model. This one will give you the desired starting location. So once you've set one, the other ones you'll let Simulink resolve and solve the angles for all the other joints in the system. So now we've got that joint, we can then create another joint, and we'll continue off, and we can do this joint, and this will be joint at C. We can flip this block, and we need another beam starting at E and going to C. So we'll just edit those names. So we call that EC, and that's going to be 80 centimeters. Well, so that's 80. Okay. Just double check that one. That needs to be 80. Yep. Right, okay. And then we just need to join those two together, and also add a solid point, and we'll call that point C. So we can place that here. Okay, so all of our beams have a bit of a mass, they've all got the correct dimensions, and we've got solid points just representing the joints. So if we go to diagram, update diagram, let's see, oh, we've just got a slight error, and that is because I've made a slight error. I have not put a joint on this side, so it can't spin and it can't actually move into position. So we just need to add a joint in that position there. So I've clicked and copied, added a joint, and we'll call that joint at E. Okay. Just double check we have no state targets in them. That's all good. And actually, just to make it a bit more obvious of what these joints beams are, we'll change this one to a red joint, red beam. I'm sorry. So we've got RGB codes, and they're from 0 to 1. So this is 1 for red, and you've got 0 green and 0 blue. Okay, so that's all okay. And we'll do the same here, and we'll have this one as a green beam. So we can see in our Simulink model which beams are which. Okay, there we go. So now with the new joint in, so we've got all the joints in, we can update the diagram. And there we go. So now it's resolved all those positions for us. It's automatically joined up all the beams for us. And yeah, it's managed to meet our ideal state target of 120 degrees for joint A. The last bit is actually kind of to add the almost a wiper element. If you could imagine this, it could be some kind of wiper mechanism. Right, so that's our beam D to C. But we do not want it to actually rotate around the joint at C. So to not let it rotate and actually just follow on from C, we can then just copy this beam and just not let it pass through a joint. Very similar to the issue here. We had no joint here, so it couldn't rotate. So now we've got this position with the joint, and it's going to come off, it's easy, and it's just going to go continue straight on. So imagine it following this red line and just continuing straight on, and that's what it's going to do. So if we go to this, and we're going to keep it red, and we're going to change the length to 30 centimeters, and we're going to change the name D to C. Okay, so C to D. Okay, so it's always good to try and say left to right, so always name it in that convention. And then we're just going to put our point mass, another point mass at the end of that, and we're going to call that D. We'll leave that on there. So I'll just bring those all back into view. And yeah, like you say, you can take quite a bit of time over just trying to clean up and neaten all these joints and lines. So it's really easy for us to see how your model works. So there we go. Okay, so now if we update that diagram, so simulation update diagram, we can see now we've extended E to C with C to D, and it's actually fixed. There's no joint in between those, so it's just continuing straight on as if it was a beam with a joint, a pin pin joint in the centre of it. So now we're all pretty much set up. We just need to run the simulation and see if it rotates. So we do that. Now it's all the masses, and there we go. So we've got no torque, it's just acting on gravity. And as you can see, it's just racing back and forth, back and forth. And because we haven't got any friction in the system, it's just going to have this continual perpetual motion. There's no actual loss of energy in the system. Now, like I say, if you were going to add your feedback mechanism, you need to pick which joint you're going to have your feedback. So let's say joint A. And what we can do is go edit and actuation, and you can add an input of torque. And remember, for your motor feedback, you're going to use the sensing and probably use the velocity of the joint to work out what motor torque you're generating at that speed. But in this case, we're just for a quick demo, just to show you how to add some torque to the system here. We're going to have a torque there, and if I open up the mechanism blocks, let's see if we've got one there. We do not have that block in this template because you won't really be using it in. I need to save that. We won't be using it in your system. All we do is actually double click and we can actually add a constant. There we go. So that's just going to create a block for us, just for this demonstration. There we go. Just let it load. There we go. And what we're going to do is set that torque to, let's say, for example, oops, I need to use remember a SPS converter, because it's a signal we're going to put into a physical system. So actually I just need to get those blocks again. So I just need to copy, paste that across. And we'll give that maybe a 2 Newton meters and see if that's enough to make it actually rotate against gravity. So let's see how it goes. Actually, yep. So we're going at a very fast speed, and actually it's come up an error because we're going so fast that it's actually unable to resolve it when it gets to a high speed. So actually, if we go against gravity here, maybe at, let's say, try 0.1, let's see, -1. So actually that was going with gravity there. Remember our sign conventions. And that's just not enough power to get across. Okay, so that's what we're going to do. We're going to have your feedback and go overcome this gravity and deploy your mechanism. Okay, so I believe that's all. The only aspect I want to add as well is there might be some cases where when it tries to create the model, it might create it in the mirrored profile. There might be cases where you could have two solutions to your angles. So if you want a particular angle and you kind of know where that angle should be, it's good that you can actually go into the joint and back to state target, specify a target, and rather than high desired, you go low approximate and say, I know it's going to be roughly, maybe let's say 110 degrees for this one, as it's E to C. And that'll encourage Simulink to pick that solution over a mirrored solution. And actually, there you go. So there's just an example of, I've just added that joint. It's actually changed the angles completely there. Okay, so you can use the state targets to try and move and choose a more favourable solution. So let's try 90 and see what happens there. Okay, so it still likes that one. Let's try 270, see what happens. There we go, so that's us rotating it and putting it back into that position. Okay, so that's how we can use the low approximate just to encourage it to flip over from one side to the other. Okay, so that's all all the blocks and all the skills that you'll need in Simulink to be able to create a multi-bar mechanism and all the information to do a feedback loop for your motor and gearbox. Well, thank you very much.